Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everyone. It's my pleasure to introduce Yaron Singer, who's a grad student at Berkeley, advised by Christos Papadimitriou. Yaron got the MSR fellowship and also the Facebook fellowship. So he has a fellowship double. And he is going to tell us about mechanism design and social networks, but a fancier title.
Thanks. Can you guys hear me all right? I mean, in the room and also. Thanks. So thanks for Nikhil and Eric, who unfortunately couldn't be here. I've been for hosting the visit. I wanted to come and give this talk for a while, so it's really great to finally do it. So I'm going to talk about how to win friends and influence people truthfully. The title is a bit scary, but so for those of you who don't know, this is a title from a book from the 30s. It's kind of a classic book for MBA students. And the book is called How to Win Friends and Influence People. So I didn't come up with it on my own. So basically today we'll talk about influence maximization problem. And we'll start off by talking a little bit about giving some examples and then defining it. And then we'll talk about why there's kind of like an inherent information and completeness aspect to the problem that we'd like to address. And once we'll do that, then I'll try to convince you that taking a mechanism design approach to this problem is a good idea. And we'll see that we can actually design mechanisms that give us these good theoretical guarantees. And we'll talk about some of the difficulties that kind of that the setting introduces to mechanism design and how we can overcome it. And then finally, we'll also talk about some experimental evaluation that we did on these mechanisms, and then I'll try to convince you that not only we get these theoretical guarantees on them, but they actually perform pretty well in practice. So just to jump to an example, so basically the influence maximization problem is basically we're asking ourselves this kind of this kind of very this question that seems very important right now, and it's how do we select a subset of individuals to recommend, say, a product to their friends so that basically the word of mouth effect or the influence is maximized in the social network. And what's really striking is that this question was asked by Dominguez and Richardson, where Richardson is Matt Richardson from here, already back in 2001. And this is kind of, if you think about it, it's remarkable because this is kind of before the time of online social networks, and but they kind of identified that this is an important problem and kind of worthwhile for computer scientists to pursue. So, kind of think of a hypothetical scenario. Suppose that we have some sort of site that has $1,000 worth of coupon codes to give. Let's say it's Zynga money, okay? And the site wants to is willing to give out the coupon codes to its users so that they recommend the site to their friends. Okay? Let's say they recommend to their friends by posting on Facebook. Just kind of a hypothetical example. So the question is, how do we decide, how to pay, how to give people the Zynga money to recommend to their friends? So to continue with the hypothetical example, suppose we have Eric, Nikhil, and Peter, right, that are coming to our site, and using it, and we know that they have friends. We can maybe look at their Facebook profiles, and we see that they're kind of connected not only to the people in this building, but their connections span wide to New England and also SVC. And basically, now we have to kind of decide who we're giving away the money to, and how we're going to distribute it. So when we take kind of just even by this example, it's not that trivial because we see that Eric is, has a very high degree, has 4 friends on Facebook, and and then both Nikhil and Peter have have two friends, and we kind of have to decide. So it seems logical that we would choose Eric, but then we kind of need to decide between Peter and Nikhil, and we somehow have to make a good decision, right? Okay, so keep this kind of image in mind, and we can talk about this in a kind of more formal scenario. So basically, we can talk about this in the simplest model. This is the coverage model. Okay, so in the coverage model, we have n agents, and an agent would be someone like Eric or Nikhil or Peter from the previous example. And each agent now has a certain cost that's associated with recommending the product. And they also have a reachable subset. And the reachable subset in this case was just their friends. Okay? And our goal is we're given some budget, B. So this is $1,000 from the Zynga money that we had. And what we want to do is we want to find some subset of people to recommend the product so that the union of the reachable set is maximized. Okay, so we want to reach out to as many people as we can with the Facebook recommendations. Yes, please.
The CI is the cost of reaching the whole set, or just one element?
So the question is, what does CI represent? So CI, so we assume that each agent each agent has a certain cost that's associated with them. So for Nikhil, for example, the cost could be like, for recommending, would be $500, and maybe for Peter, the cost would be $50. So it's individual to each agent.
No, that wasn't the question. Is it the cost of reaching the entire subset RI of friends, or just one?
Oh, I see, I'm sorry. So it's just the cost of posting a recommendation on Facebook. Just making a single. Yes. Yes, in this example, reaching the whole subset. Yeah. Okay, so this is kind of the coverage model, and just kind of more generally, we can think about general influence maximization problem where we have n agents, and again, each one has a cost. But now we have instead of a reachable set, we have an entire social network, and there is what we call an influence model. And an influence model is just is simply just some probabilistic rule that tells us how messages propagate from one person to another. Okay, so it's the probability that you're influenced given that your friend is influenced or made a recommendation. Okay, and the goal, in this probabilistic model is basically similar to the coverage model. We're given a budget B. And basically, we want to find a subset that will maximize the expected number of influenced people in the social network. So what I'll do is I'll stick to the coverage model, and I'll talk about things in the coverage model. And then kind of towards the middle of the talk, I'll just kind of tell you that most of the things that we talked about here extend to this, to the more general settings. And I'll explain which settings and how. Okay, but just for simplicity, it's good to think about the coverage model because it's kind of a simpler setting. Okay. Yeah.
So you're assuming there's no propagation of influence?
Yeah. So right now, in the just for the kind of the purpose of making things concrete, I'm thinking about the coverage model where there's no propagation. There's no propagation, and everybody that you're connected to is immediately influenced. Everything I'm going to talk about will also extend to the more general settings where things do propagate. But just kind of for concreteness, we can just think about the simple setting. Okay. Good. So kind of let's just try to give an overview of what's, it's been a decade. So the main research directions thus far have basically been in, I think you can think about them in three categories. So the first one is about characterization of influence models, right? So and basically the fundamental question is what sort of influence models allow for tractable optimization solutions? And kind of a very seminal work was by Kempe, Kleinberg, Tardosh in 2003. Basically said, well, for most problems that or in general, this problem is not only it's NP hard, but it's also inapproximable. But it seems like, but they identified this class of influence models that were very fundamental and been studied in literature that had these submodular properties. And what that means is that when they show that when you have an influence model that's modular, then you can just apply a standard greedy algorithm which gives a 1 - 1 over E approximation. So the problem is hard, but you have a lot of models that you call submodular influence models, where you can apply a simple algorithm and get a good approximation ratio, 1 minus 1 over e, which is roughly 63%. And it can actually show that there's a lower bound, so you can't really do better than that. Okay? And these models have been even extended further to show that more and more that there's a larger class of these submodular influence models. Okay? And I'll talk about the main models of. Well, the lower bound applies to the coverage model, which is kind of basic fundamental one. Yeah. But that's a. Yes?
So by influence models, so for instance, the coverage model is an example of an influence model.
Yes, exactly. I mean, the coverage model is like a deterministic influence model. Yeah. Okay, and then kind of another direction of research was about actually inferring influence models. So you're saying, okay, I have a lot of data, and basically now I want to understand, like, try to fit the right model that will explain how people really influence one another. And then kind of the third direction is actually about computational techniques, saying, how do we solve this problem at large scale? We want to apply this to online social networks. This requires a lot of computational power. How do we use these methods, to really scale? Now, the fundamental assumption in this problem, and which kind of require for all these techniques, is that individuals have costs, and these costs are their costs for making a recommendation to their friends in the social network. And basically, inherently there's an incomplete information aspect of having this cost, because it's very hard to extract. So all the techniques that we're talking about basically rely on either the costs being explicit, so they're explicitly given to you as part of your algorithm. So your algorithm receives as input the social network, the cost of each person to make a recommendation in the social network, and then an influence model. And then based on that, you compute an outcome. Or they somehow assume that it was implicit, that there's some way from data to learn what the right threshold cost would be for people to make a recommendation, and based on that, compute some sort of solution. Okay.
How would you calculate that?
Right. So you can. So first of all, I don't know, right? But you can. But this is an assumption, right? So I guess what I'm guessing the assumption is that you assume maybe you can do a survey, and then after you do a survey, then you sort of you do a survey of people's costs, right? And then you kind of somehow find a threshold cost that people would, you find like the optimal cost that people would have, right? And then you decide, okay, I'm giving everybody, this much money, and you can either take it or leave it.
So in other words, you're just not getting into the sort of game theory problem where people have costs which they're not willing to tell you.
Mm-hmm. So kind of what are the what are the challenges when that we expect when we don't know the people's costs? So first of all, your first job might be to say, well, maybe we can try to predict costs. Maybe people we can sort of profile people, right, and then based on their profiles try to guess what their cost might be. Well, the problem with that kind of approach might be that it's just going to be very, very hard to do. People would have, as we'll see later, people have like very, very different costs for making a recommendation, and those costs might depend on, just many, many parameters that are very hard to extract, like a personal history of a person, their affiliation with a product, just many, many other things, and that can have an extreme influence on how much their cost is going to be. And it'll be very, very hard to predict. So the second approach would be doing something like a survey, right, where you'd survey people and try to determine the threshold price out of that. And the problem is that even if you can do like a good survey, then you can actually show that this kind of approach would give you poor solutions both theoretically and practically. And I'll talk about that later. Okay? So when you compare it to what you would be able to do if you actually knew the costs. Okay? And finally, you can just naively go to people and ask them how much they want to be rewarded and, and pay them. But essentially, if you do that, then you run into the risk of people actually lying to you, right? Because if I know that you're going to pay me what I asked for, so maybe my cost for making a recommendation is 20 Zingo dollars, but maybe I'll say it's 50 or 1,000, right? So that's kind of that's the thing that we need to get around. So in this talk, the question that I'm interested in asking is, can we design algorithms in this environment where we have incomplete information that will still give us good solutions? Okay. So to do that, we'll do this using a mechanism design approach. So, and what does that mean? So it means that we're going to assume that agents are, shows you where my mind is, that agents are rational, okay? And all that means is that people want to maximize payment minus cost. So that's a standard game theoretic assumption. So if we assume that they're rational, then and that they have these private costs that we just don't know, then what we want to do is mechanism design says, let's design mechanisms that incentivize everyone to declare their true costs. We'll do it in some magical way so that we know we pay people the right amount and we select people in the right way so that everybody tells us exactly how much their real cost is. And a mechanism is just a big word for an algorithm plus a payment rule. Okay, so basically what we need to do is we need to design algorithms and tell you and kind of say what the pay rule is going to be. And we're going to have some restrictions on these algorithms so that we can actually get the solution that we want. And the procedure will look something like this. We'll have a social network. People will tell us how much they want to be rewarded. And we'll incorporate all that into our mechanism. And then our mechanism is going to eat all that information and then select the lucky few and give them payments. Okay, and give them Zingo dollars so they can tell their friends. Okay. So, and for the rest of this talk, what I'll do is I'll talk about mechanisms for the coverage model, and I'll tell you what the difficulties are in designing these mechanisms, and but also I won't leave you hanging. I'll also tell you the main ideas and how to solve how to solve the the interesting problems there. Then I'll, like I promised, then I'll tell you how they extend to other models as well. So it's not just the coverage model. And once we do that, then we'll talk about we'll show some experimental evaluation on these mechanisms that show that they actually work well in practice. Okay. Okay. Good. We're good with time. So just again, what the setting in the coverage model in the mechanism design setting, then we have n agents. That didn't change. Each agent has a cost, and we're saying now that the cost is private. And what that means is when it's private, we don't have any information on their cost. And our goal again is we're given some budget B, and want to select subset of agents that maximizes the coverage under the budget, and we're going to restrict ourselves to mechanisms that are computationally efficient. So we're still in in algorithmic perspective. When a computationally efficient mechanism basically means that its algorithm and the payment rule need to be computable in polynomial time. It needs to be truthful, and that's just another word for incentive compatible. So it needs to provably be able to elicit the true costs from the agents. And then the important thing is that it needs to be budget feasible. And the budget feasibility here means that the sum of the payments needs to be under the budget. So the fine point is that we need to restrict ourselves to when we're in this setting, then the payments are always going to be more than the costs. And we need to be able to design mechanisms that the total budget, the sum of the payments does not exceed the budget, and not the sum of the costs. So we'll talk about in the next slide. And then finally, our mechanisms just need to be good in the sense that they approximate the optimal solution well. Where the optimal solution would be, the optimal solution that we would get if we knew everybody's real costs and we didn't have any computational limitations. Okay, so this is kind of the standard optimal solution that we would compare against. Okay, so this is kind of the most strict conditions that we can impose. Yeah.
So can you comment on why you want to insist on truthfulness? I know it sort of seems reasonable, but you might say all
right.
you care about is maximizing f
right.
with something
right.
in your
I mean, I think that's okay. That's great. So why should we? So the question is, why should we care about truthfulness, right? And why should we insist on it, right? So so first of all, that's a philosophical question, right? But I think the short-term answer is because we can. In the sense that, well, if I came up and said, well, I have an impossibility result, then that would be one thing. But actually, if we can actually design it in such a way that will actually get us the true values, then that would be great. But more serious, but kind of to give you a better answer, if we don't insist on truthfulness, if we kind of think about like different, then we'd have to think about a different solution concept, right? And we do know that there are problems where we can't design truthful solutions for, and then we have to resort to different, then we have to go to different solution concepts that are worse than truthfulness. And then the biggest problem that they usually have with concepts like Nash equilibrium and things like that is that it's very hard to predict what people would do. And then it's hard to sort of justify that you have a solution that's comparable or good with what you would get otherwise.
And your definition of good there is that sort of in the very strong sense that you're hoping to get something that's truthful and
yes.
It's even almost as good as non-truthful.
Yes, exactly. Okay, so kind of what's hard about this is, well, the first thing about that's hard is really having this budget constraint on the payments, and that's that's a challenge. Okay, so and it's a challenge. First of all, well, you can just show that the optimal solution basically just exceeds the budget by enormous factors, and that's you can construct like very simple examples that show that. And well, when you look at approximations, then you can construct these simple natural settings where you show that once you restrict truthfulness to be under a budget, then you get just horrible approximation guarantees. So the budget is a really big challenge in the setting that needs to be overcome. Okay, and then the second challenge that I'm going to talk about is basically is an approximation challenge, where in all these settings, to get a good approximation, we need to be able to run two different solutions and then take the maximum between them. And that's just something that naturally comes from the fact that we have a budget constraint, not an incentive compatibility sense, but just a standard algorithmic sense. And then the problem is that once you try to apply the maximum to solutions in this setting, then it breaks incentive compatibility. So these are two major challenges that need to be overcome in order to design an incentive compatible mechanism for this setting. And we'll talk about the way to address these is to address the payment constraints. We'll talk about the setting that's called budget feasible mechanisms, and those are mechanisms that give you truthful approximations who can actually do us what, get us what we want. They can guarantee us that the payments will never exceed the budget, and they run in polynomial time, and they're incentive compatible. And to talk about what we're going to do with the maximum issue, then we'll talk about how you can use nonlinear programming relaxations in order to circumvent that problem. So those are the two things that we'll talk about. So first of all, we'll talk about how we deal with the payments constraints, and then I'll talk about the incentive compatibility of the maximum operator. Okay? Good. So in our mechanism, we're first going to address the issue with payments. We'll use the proportional share allocation rule. So the proportional share allocation rule is just something that's just very, very simple. And it just has 3 stages. The first round, round 0, we start with the empty set. And then the second round, we're going to choose an agent to add to our set. And that agent is going to be the one that maximizes this quantity. And what this says is it's when we evaluate the function on the set S. In the first case, it's the empty set of the agent minus the set that's already been selected divided by their cost. So this is really the marginal contribution of the agent divided by their cost. And the intuition for why we want to use this kind of marginal contribution ordering is basically because we know that using this approach is what gets us good approximation solutions in the greedy algorithm. So the greedy algorithm, in the non-incentive compatibility setting, we just greedily choose agents according to their marginal contributions, and discontinue once we exhaust the budget. So at each stage, we're going to choose the agent that maximizes the marginal contribution. And then we're going to decide whether to add it to the set or not based if their cost is less or equal to what we call the proportional contribution. And the proportional contribution is their marginal contribution divided by the value of the entire set if they're included. So the intuition that kind of comes from where this comes from is cost sharing, where basically we want to add people to our solution only if they can justify it in the sense that their contribution over the value of the entire set is larger than their actual cost. Okay, if they contribute more than they account for, intuitively. Okay. There's no budget. So the assumption is that the budget is normalized. Everything is normalized, and the budget is 1. Right. So you can.
So where is the right side is dimension and the left side. So where is the budget normalization?
Here, the budget should multiply.
Mm-hmm.
Okay.
So CA over B on the left.
Yeah.
Okay.
Yeah. The CA. Yeah. So.
Why is it denominator? If f minus f is bigger than CA, then you make money paying A to increase the function. It doesn't matter how big f itself is, right?
Well, there's no relationship between like how much happiness we have and how much cost the agents have. I mean, those are kind of like 2 different worlds. We can think of like in 2 different quantities. Right? But yeah, it's. Okay, so this is a proportional share allocation rule. Start with the empty set, take order agents according to their marginal contribution, and then take them greedily if their cost is less than their proportional contribution. Okay. So the reason why this allocation rule is so wonderful is because we get these 2 nice lemmas from using it. The first one being that it's just a good approximation guarantee. So basically, for any submodular function using this proportional share allocation rule, we can show that it's a constant factor approximation of the optimal solution if we remove the item with the largest value from the set. Okay, so under this assumption, then the proportional share allocation rule is great. Gives us a constant factor approximation guarantee. Okay, And the second, and the more important reason for why we would use this is that we can show that for any submodular function, the proportional share allocation rule is, first of all, incentive compatible. And the second thing is we can show this nice property about the payments that this sort of allocation rule leads to. And the payment property is this. Okay, so if the payment is theta, then we can show that it's basically only a constant factor away from the proportional contribution of that agent. So, why would this be good? Because what we can do is when we sum up all the payments, when we sum up all the thetas here, then we know that they're bounded by constant factor times the budget. We just move the valuation of the entire subset here, and then we sum everything up, and it gives us a constant factor times the budget. So basically, the proportional share allocation rule leads to payments that are basically will exceed the budget, but not by a lot, only by a constant factor. Okay, and the way to prove that is we can actually we can characterize the payments, which is a bit more involved, and then once we characterize the payments, we can show this property that they're bounded by. When we sum them up, they're bounded by the budget. So what we can do is we can run the proportional share allocation rule with not the budget, but we can shrink the budget by this constant factor, run the proportional share allocation rule, still get a constant factor approximation because we only shrank the budget by a constant factor, okay? And then guarantee that the payments don't exceed the budget. Does this make any sense? Yeah? So, I mean, it's kind of, I didn't tell you, not proving these lemmas, right? So, it's not immediate to see why this is true, but you'll just have to take my word for it, and just see that, basically the conclusion is that the proportional share is, gives us a good approximation guarantee and doesn't exceed the payments.
So this constant depends on what?
And I mean, this constant is, it's, I mean, it's a constant. It's like it's a universal constant. Yeah, and I can tell you, kind of give you an intuition later for where it's coming from. Yeah. It's, I mean, they're just ugly, and they vary by the different settings. So I just.
So they vary by the different settings.
So for any submodular function, you can show global constants of. I think this constant is 2, or this constant. Well, depending on the setting. Okay. But. Okay. So the conclusion is that it's good because it gives us, payments are bounded, gives us a good approximation guarantee. But we're still assuming that we still threw away the agent with the largest value. So we need to somehow be able to, in an incentive-compatible way, decide which solution is better. Okay, and once we'll be able to decide whether the proportional share allocation rule or the agent with the highest value is better, then we'll have a complete constant factor approximation guarantee, and we'll be done with a theory. Okay. So to show us how to do that, then I'll explain to you just why, what's the problem in taking the maximum in this sort of setting. So basically, an incentive-compatible mechanism is you can essentially characterize it by a rule in this setting, by a rule on the algorithm itself. Okay, so Meyerson in 1981 gave us this amazing theorem that tells us that in these settings where we have what we call single parameter settings, where the private information is only a single number, like in our case, then an algorithm or a mechanism is incentive compatible if and only if its algorithm is monotone. And the monotonicity is basically says that if I have an agent with some cost that's been selected into the solution, so as long as nobody else changes their cost declaration, then the agent that was selected can reduce their cost and still be selected by the algorithm. Okay, so in our case, reporting a lower cost can hurt you. So that's the monotonicity property. Does that make sense? No? Okay, so in our setting, right, we have people declaring cost of the mechanism, right? And if you think about it, the lower somebody's cost is, right, the better it is for us, right? Right? Then we can put more people into our solution. So the monotonicity rule says that an algorithm is monotone if you have some sort of agent which is the algorithm which is selected by the algorithm, right? And now, if that agent reduces their cost, declares a lower cost, and everybody else declares the same sort of cost that they declared before, then that agent must get allocated into the solution. You can't. My algorithm can't hurt you if you give me a lower cost. Then you're only helping yourself in the competition. Okay. So in order for an algorithm to be incentive compatible, then it must respect this monotonicity property. And the problem is that when we apply the maximum, that just violates the monotonicity property of the algorithm. So I'll give you just a quick example. So if we go back to our friends here, okay. So what we would do is we want to run this algorithm, and with taking the maximum out and seeing how that hurts us. So we put Eric away because he has the highest degree. Okay, so he's the maximum. And now what we're going to do is we're going to run the proportional share, or basically any greedy algorithm, on Peter and Nikhil. So the way that happens is Nikhil comes up and says, my cost is $2. And then Peter comes up and says, well, my cost is $1.5, right? Nikhil, in this case, Nikhil gets selected, and then Peter gets selected. And then they both have the value that they produce is as large as Eric's, so we're going to select them into the solution, and they're both selected. Now, if Peter declares a lower cost of 0.5, so Peter changed his cost, and now we need to recompute the mechanism. So now when the mechanism gets recomputed, then we can come up with an example where Nikhil can no longer be in the solution, because basically they come in, Nikhil now comes into the solution second. Their contribution doesn't respect his contribution before was, when Nikhil came into the solution first, his marginal contribution was 2. If Peter gets selected first, then Nikhil's marginal contribution drops to be 1, no longer justified by the proportional share allocation rule, or and you can also show this for other algorithms. And then Peter is stuck in the solution alone. And then when he competes with Eric, then Eric has more friends, so Eric wins. And you can kind of try to play with all these sort of examples and try to put some weights on them, and but you're still going to end up in the same sort of situation. So somehow you need to circumvent that. So Eric gets in the solution. So basically, what we can do is for the coverage problem, we can actually formulate this as an integer program. Okay, so this is what I wrote here. It's not that important how you formulate it, but basically the important thing is that what we're trying to maximize here is ZJs are variables that are describing the the people that get covered, and that's what we're trying to maximize. So you can take this integer program, and you can write a relaxation for it, the following form. So this relaxation is different from the integer program in two different ways. The first being is the objective function that we're trying to maximize is different. So it's not just a linear programming relaxation. So we're actually changing the objective function. But you can show that on when your solutions are integral, when your solutions being the x's that you choose here, when they're integral, then this program would give you the same solutions as this sort of program. And the second thing where they differ, of course, is in the integer program, we're restricting ourselves to solutions that are in 0, 1, and in the relaxation, we're allowing ourselves to have solutions and on the real. Okay, so we're basically now we're going to take the idea is to think about the coverage as an integer program, and then think about a relaxation. The nice thing about the relaxation is that we can compute the optimal solution in in polynomial time. But it's going to be a fractional solution. So what we're going to do is we're going to find the optimal solution of the linear programming relaxation, okay, over the subsets of the agents. And then if the relaxation solution is greater than the agent that has the highest value, then we're going to take the proportional share allocation rule. And if not, we're going to take the agent with the highest value. Okay? So instead of comparing directly between the proportional share and the agent with the highest value, we'll just compare the relaxation. And if the relaxation has a higher value, then we'll take the proportional share. Okay? And the reason why this works is the mechanism this now is monotone. And the reason being that now an agent, if they decrease their cost, then the value of the relaxation is only going to go up. And the reason being is because we're computing the optimal solution over, and it's fractional. So decreasing your cost can only help the optimal solution in this case. So we don't run into the problem that we ran into before. And the second thing is now you can show that this mechanism still now gives you a constant factor approximation. And the reason is basically because you can show using pipage rounding that the solution of the relaxation and the proportional share allocation rule are close. And if they're close, then when you're comparing the relaxation rather than the proportional share, then you're only losing a constant factor. So you show that with pipage rounding that the relaxation is constant factor away from the optimal integral solution. And then we know from the previous lemma the proportional share is an approximation to the integral solution. So we're good. Okay, so the conclusion is that we can get the main theorem says we can get a mechanism for the coverage model, which gives us roughly a 22 approximation, which is budget feasible, incentive compatible, and what else? Runs in polynomial time. Okay, which is so great. We're there. So we have a good solution. And now, kind of one slide for why this is good. Why this talk is not called on maximizing coverage models. Well, basically, there are two main models that we're studying in literature: are independent cascades model and the linear threshold model. So the independent cascades model is an influence model, and the rule is very simple. Basically, each agent has some probability on how the rest of the agents in the social network influence it. Okay, so if Nikhil recommends something to me, then the probability of me being influenced is, say, 0.3%, 0.3, and if Peter recommends something to me, then I'm sold. It's it's probability 99 that I'll be influenced. Then there is the linear threshold model, which is a bit more intricate, but there each edge in the social network has a weight. Nodes choose a threshold at random, and then if the sum of my influenced friends exceeds the threshold, I'm influenced, and if it's not, I'm not. Okay, so these are just two probabilistic influence models. They're kind of like the main ones that have been studied in literature. And in both models, we can show that in every realization of the probabilities, then these models reduce to the coverage model. So we can go back and apply the mechanism that we just saw on these two models and get the same guarantees. And just in general, for the set of kind of feasible influence models that we can get are the submodular influence models. And for those, we can basically show randomized mechanisms that give you constant factor approximation guarantees and expectation. And for some cases, like the voter model, you can actually get mechanisms that have better approximation guarantees than the one I showed you before, like approximation ratio of 4. So conclusion is for various influence models, we can tweak the mechanism one way or another and get a good approximation guarantee. Okay? Yeah?
I'm not really following the reduction. So, I mean, how would you needed the RIs in order to run the algorithm, right?
Oh, sorry, what?
When you ran your algorithm in the coverage model, you took as input the RIs, which is how many neighbors they had. I mean, you can't really compute those, right?
Right. So what I need to do is I need to decide I need to flip a coin, and then basically I have a realization of the probabilities. Yeah. I have a sample, right? And then on the sample I construct the reachable set. These are the RIs, and then I reduce it back to the coverage model.
And that whole thing will be polynomial time.
Yeah. I mean,
that was polynomial time, but it wasn't clear that with one sample you're going to get.
Oh yeah. No, I mean that's why it's a subtle point because right. I mean when you sample once, right, then you're right. You want to argue that it's not clear that with one sample in expectation, right, you'd be able to sample once, right, and get a good approximation guarantee. Oh. But if you can, then if you want to avoid that path at all, then you can just randomly choose between, the maximal element and the proportional share solution, and then choose randomly between them, and then get a constant factor approximation in expectation.
Okay, I'll take it.
Okay.
Confused.
Okay, so I convinced maybe some of you that that this works for other models. Okay, so we have when we have like a kind of good theoretical guarantees, I think the nice question is whether this actually holds in practice. Whether the guarantees that we get are in practice are meaningful, and maybe they're like just much simpler methods that we could have applied that would have save us all the trouble and just be better or comparably or just be comparable, right? So how good is good and how bad is bad, right? So we want to evaluate these mechanisms in practice. So for network data, that's we're very lucky, right now because we live in an age where getting network data is something that's rather straightforward, and it's so straightforward that even a person in a theory group can actually go and get data, and you can and here I just took samples of Facebook graph. This is a public data set that's been from a group from Irvine, where they sampled the Facebook graph through random walks, and they got us a graph of almost 1 million nodes and 72 million edges. So it's a huge graph, right? And it's a representation of a social network. And for influence models, then we're lucky to have strong computers that basically can generate simulations. Right? We can feed them influence models. We can and then generate these simulations that would kind of tell us like how many people are influenced in different models. The crux of doing something like this is basically how do we get reflective costs? So we started this talk by saying, oh, getting costs is something that's so difficult to do and so hard to predict and blah, blah, blah. Then, we want to somehow have some sort of meaningful distribution that would kind of reflect people's real costs for making recommendations in the social network. So how many people are familiar with mechanical Turk? Everybody? Nobody? Somebody? OK. So for those who are too shy, so mechanical Turk is this nice platform where requesters, who are people like me, create tasks. So they have an interface like this that you can change some parameters and basically create these tasks for people to work on. Then you have workers who log in, and they work on multiple tasks. And this is what their world looks like. Okay? They have this list of tasks, and they can go off and choose which task they want to work on. And traditionally, it's been used for things like, well, for anything, but people use it a lot for things like image labeling and sort of these tasks that you need like some sort of human intelligence in the process, and you want to get it done at large scale. So this is the task that I posted on Mechanical Turk. And I'll just give you a second to read. OK, so this is what it looks like. Has the title, says we're giving away bonus money. So this is a competition that we ran on people on Mechanical Turk, and basically asking them, how much would you like to be rewarded for posting something like this on your Facebook profile? So they gave us bids, and the bids were from 1 to 20. That was the range we restricted them to. And then we asked them, how many friends on Facebook you have? And that was it. That's it's called the hit. That was the Mechanical Turk hit. Click on submit, and then we get that information. So so the goal was to establish a real distribution that we can use to match with the network data that we can run the algorithms on, right? So the experiment ran for a period of about 3 months, and I paid people from the range of 5 cents to 50 cents. I kind of played with it to see, yeah?
It says it costing from $1 to $20. Where do you get the cent amount?
Right. So I asked people to bid on how much they want to be rewarded for posting the message on Facebook. But in order for them to, I needed to pay them to work on the actual hit. For the fact that they click on submit, I need to pay them something. And then but they understood that in order to get what they to get something that's as high or higher than what they bid for, then they would actually need to post this on Facebook. So we pay people like within this range, and average payment was about 26 cents. The question was whether are they affected by the payments, right? And the answer was no. We got the same distributions no matter how much you pay them. Collected roughly 1,500 bids, and about 1,100 of them came from unique Mechanical Turk users. So posted for over the period of time, continuously posted the task, so people repeatedly. Some people came worked on the task again and again. Then the profile was restricted to people U.S. residents and that had a quality score of 97% or more. So if you're using Mechanical Turk, then you maybe have some sort of estimate what that quality score means. OK, so now I'm going to show you some plots, and just don't worry, no irritations or hurt making these. OK, I mean I did them, but I wasn't hurt. OK, so the first question was, is there any strategic kind of correlation between number of friends that you have and costs, right? And the question was, if it turns out that there was some correlation between how much people bid and how many friends they have, then that would somehow have to be reflected in the experiment. when we see like if we get an experiment, we get a node that has a high degree, then we somehow need to adjust the distribution that we're, the cost distribution we're assigning for. And so the answer is no. This is the plot. I played with it. I tried to bin it in different ways. There was really no apparent correlation between the number of friends and the bids and people's cost bids. I mean, this is, I'm sure there's kind of more, statistically more significant ways to say this, but this is, I'm saying this with the plot.
There's something weird about these people. They don't have very many friends.
Oh yeah, this is the friend category. I bin them, right? Because everybody declares like a different. Everybody has like a different number of friends, right? So I bin them into categories of 0 to 100, 100.
There's something strange about the dots as well, because it doesn't look like 1,500.
I'm sorry?
That doesn't look like 1,500 dots.
Yeah, when they're binned, I just average them.
Oh, so some of those dots have a lot more weight.
Yes. I mean, I can show you the regular plot, but. Yeah, I mean, there's really. I wish there was, actually. And then the question, maybe people lie about their friends, but actually, when you look at the distribution of the number of friends, it actually this is pretty much where you get when you run BFS crawls on Facebook. So I think regardless of this, something that's interesting is you ask people for how many friends they have, and you have no way to verify if people lie to you about if a particular person lied to you about how many friends they have. But when you aggregate everything together, then you get this distribution that is that seems to be reflective of what's really going on. Okay. So how kind of the other interesting thing was like how complicated is it for people to bid? So on average, hits were completed within 32 seconds, right? And this is what the distribution looks like. So people kind of, I think my version is that they got it pretty quickly. Somebody's version might be that they didn't care pretty quickly. I mean, okay. But both stories seem plausible. But really, there's no. I looked at whether there's any correlation between bidding times and costs. Whether kind of people that maybe bid $5, $10, $20, like spend less time on the task. But again, there was just no correlation. So I don't know. And by the way, people like emailed me back, like asking about, when is it going to be, when is it going to be decided? I already posted on Facebook, blah, 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 all this sort of stuff. So that was interesting. You also get to make friends on this mechanical Turk. It's not just research. So then, finally, what does the cost distribution look like? So it looks something like this. So, I mean, this is something that, if I generated this without telling you that I did a mechanical Turk experiment, then, I mean, I just don't really know what to make of it. So, but it is what it is, right? And roughly a quarter of the people bid, the maximum bid, which is $20. Quarter of the people bid below $5, and then everybody else was kind of in between.
So these peaks are exactly 5, 10, 15, and 20, right? Because those are kind of popular numbers.
Yeah, but you get like a lot of the mass here, like below the 5. Right, so. And again, there was, as I said, just no correlation between time and bid value. So you get a distribution. So now, using this distribution, we can actually run the experiments. Basically, we ran 4 different algorithms. The first is the greedy algorithm. The second is a proportional share algorithm. Basically, the tweak here was you could use almost your entire budget. This is in the characterization of the payments, which determines how much of the budget you can use. Then it has these dependencies on that you can basically when you know the network, then you can kind of allow yourself for more budget because you know that you're not going to have overpayments. And then we compared this to a near optimal fixed price mechanism. So, which by the way is not truthful. So except the proportional share allocation rule, nothing here was truthful. So which is kind of, to give it better competition. So the fixed price is basically saying, well, suppose that I'm giving you, what I did is I gave the algorithm the distribution. I allowed it to find the optimal threshold value to give to people, and then it would just give this. It would just have this take it or leave it offer for people. You can show that it gives you an logarithmic approximation, and you can also show that there's a lower bound of log n over log n for any fixed price mechanism. So this mechanism is almost optimal, both theoretically at least. Okay, and the question is can you do almost as well or better by using something like as simple as just a fixed price strategy? Can you just give away can you just decide on that $7 should be your ideal value, should give everybody $7 worth of Zynga money instead of collecting bids and all that stuff. And lastly, there's just a random assignment just to give us kind of like a lower bound of what would just make sense if what would happen if you just randomly gave it to people. So, and this is what we got. So we're the green, okay? And this is just a look on different models. So so you can just kind of get a quick picture of what's happening. Basically, the blue is the greedy algorithm, so that's an algorithmic upper bound. And basically, in many models, the green is almost a factor of 2 away from the blue. And there are reasons for why that's happening. I can explain that offline if somebody's interested. But it's kind of that's what it is in reality. The proportional, except for some cases you'll see in a minute. So the proportional share allocation rule, gives you almost roughly half of what you would get if you were running in an environment where you didn't have these incentive constraints. In the coverage model, it seems like the red line is the uniform or the fixed price mechanism, and that seems to be comparable with the proportional share allocation rule when you're looking at the coverage model. These are small budgets from 0 to 500. When you're looking at other models, then then you can see the uniform price mechanism really drops. And the difference in other models is that there was some propagation. So when there was some propagation, then all of a sudden the reachable subsets became much, much larger, and then the fixed price mechanism all of a sudden has very bad performance. And in some cases you can see that this turquoise is the random mechanism. It has performance that's even lower than just a random assignment. So, the message is fixed price mechanisms are bad theoretically and practically. And you can also do this with more money. So we did this before with 0 to 500, and this is these are 0 to 5,000, and you see. And the interesting things that you see there is you see in some cases like the independent cascade models with when we have low probabilities, then you can see that the proportional share allocation rule and the kind of the greedy algorithm have almost similar performance. And again, you see that in the coverage model, this seems like the fixed price mechanism does reasonably well, but then in where there's propagation, it does really, really badly. And then just finally, just an interesting anecdote is you can also, the question is how many people you have in your system. So this is what you see. This is the blue now is our mechanism. The red is the fixed price mechanism. Now this is when we have, and this is how they perform when there are 1,000 people in the system, and they're roughly a factor of 2 away. But as we're increasing the number of people, number of bidders in the system, we're staying with the same budget, but we're just adding more people, right? So this is with 2,000 people. This is with 3,000, 4,000, and 5,000. Almost went to linear. Almost becomes just a straight line. Oh, sorry. Then anyway, then you see that there's a huge gap that's opening between these two mechanisms. Okay, so basically, increasing the number of bidders doesn't really help fixed price mechanisms, and I kind of have my beliefs for why, and I can talk about that offline. Whereas, for the proportional share mechanism, it really helps. Okay. So that's pretty much it. So just kind of to conclude, so I think my interest was to kind of take mechanism design and look at kind of different settings, in this case in the social network settings. And it seems like it just can just makes them kind of contributes to theory of mechanism design and can introduce interesting problems. We see that it's basically using mechanism design helps the social, problems in social networks. In this case, the influence maximization problem, and in this case, the information incompleteness aspect of it. And finally, we can see that with experimental evaluation, we can not only get theoretical good guarantees, but we can also get mechanisms that seem to work pretty well in practice and and perform well as in comparison to other things that we may try. So that's pretty much it. Thanks. So, any questions?
So, in your theorem, it said it was guaranteed to be a constant factor 22 approximation or something. Right. And in practice, it looks like it does much better than that.
Yeah.
Any guess as to what that difference comes from? Are there some particular bad cases that you're avoiding in the?
Yeah. So the question is why, why is it that, in, the theoretical guarantee is like a factor of 22, but in practice it does much better. So, the worst case is like when you're analyzing over, you run into like all these corner cases when you can have, one guy that has really high value, and that can really throw you off. That kind of, that creates these kind of gaps of factor of 2, factor of 4, and then you have like other cases where one person can really influence the outcome of the mechanism. That also has a large effect, and in reality, those things just don't happen. So, you can get away with good solutions. So, yeah.
Great, thank you.
Okay, thanks.